everybody, welcome back to my Gregorious Maths video. Today we're going to be looking at the fundamental group. And yes, this is not ring theory, this is algebraic topology. But this evening, I was sitting outside and I kind of, I don't know where I was sitting, but basically I just had this rush of enthusiasm for algebraic topology. And I kind of promised you guys that I would do a video on the fundamental group about 3 weeks ago. Then I completely forgot about that promise, and here it is again. Fundamental group time. Here we go, okay? But before I say what the fundamental group actually is, we have to prove that this operation here, the equivalence class on F star the equivalence class on G, being equal to the equivalence class of F star G, this operation here, the star operation, satisfies the axioms for a group. That's what we want. Or that it has inverses, associativity, and a two-sided identity. Okay. Now number one is the identity. So we want a map such that we have the equivalence class of F star that map, we get the equivalence class of F. So we'll define E sub 0 to be a constant map from 0 to 0. And we'll have I, which takes you from 0 to 1, to be the identity map. Okay? Now, if we take E0 star I, this will go from 0 to 1. And because I, the interval, is convex, okay? This means that I star E0 is path homotopic to I. Okay, because any two paths in a convex set are path homotopic. Now, do F compose both sides? It's very easy to check that this path homotopy relation respects composition. So F compose I star E0 is path homotopic to F compose I. Now, we can distribute this composition. So F compose I star F compose E0 is path homotopic to F. Okay, because F compose the identity is just F. Now, this is F star. And now whatever this map is here will be the identity, okay? Now, what is this? Well, this is, F compose this 0 map here. Well, this is just, F will take you from some x0 into x1, and E0 just goes from 0 to 0. So when we do F compose E0, we'll go from x0 to 0, okay? Or just E based at x0, because it'll actually go to it'll go to 0. And yeah, it's just E based at x0. So we have E based at x0. Sorry, that was all slanted and I don't know what I was thinking by writing that. I'll probably cut that out. Is path homotopic to F, meaning that when we take the equivalence classes, we're left with this. So we have identity, this identity, and it's not two-sided, but you can use the same reasoning with E1 to get the left-sided identity. Okay, I'm going to hope that I have enough space on the board to prove the existence of inverses. So we have I, again, which takes you from 0 to 1. And we have I bar, the inverse map, which takes you from 1 to 0. Yeah, okay. Now, I is the identity, and I bar of S is equal to I of 1 minus S is equal to 1 minus S. Now, I star I bar takes you from 0 to 0. Therefore, I star I bar is path homotopic to E0. Now, this means that F compose I, okay, star F compose I bar is path homotopic to EX0. Okay? By the same reasoning as before. Now, F compose I is F. Star, well, what's F compose I bar of S is equal to F of I bar of S is equal to F of I of 1 minus S is equal to F of 1 minus S is equal to F bar of S. Okay, so this is F star F bar, and this is path homotopic to EX. E at X0. Now taking the equivalence classes on both sides, we have inverses. Yes, I have enough space to prove both of these, and last but not least, associativity. Associativity is the longest, the most amount of work, but probably the most logical and easiest one to prove. So it's quite a fun ride, to be honest. Now, we want to prove that the equivalence class on F star, the quantity equivalence class on G star, equivalence class on H, okay, but what we're going to do is we're going to look at F star G star H. And this is equal to F star G of 2S, as long as S is between 0.5, or H of 2S minus 1 if S is between 0.5 and 1. Okay? But we can expand the top part of this piecewise function out as F of 2 times 2S is 4S for 2S between 0.5 or S between 0 and 1/4. Okay? Now, we have G of 2 times 2S minus 1 is 4S minus 1, as long as S is between 1/4 and 1/2. You can check for yourself these, I don't know what to call them. Basically the S between part, you can check those yourself. And H of 2S minus 1, as long as S is between 1/2 and 1 stays the same. Right, now, we're going to do F star G, the quantity G star H. And this is equal to F of 2S, as long as S is between 0.5, and G star H of 2S minus 1, as long as S is between 1/2 and 1. Alright, now, again, we can expand the bottom. So the top part of this piecewise function stays the same. Okay, and the bottom becomes G of 2 times 2S minus 1 is 4S minus 2, as long as S is between 1/2 and 3/4. Again, you can check that that's correct for yourself. And H of 2 times 2S minus 1, and then that minus 1, which is 4S minus 3, as long as S is between 3/4 and 1. Now, with this information, we can construct a homotopy between them. Okay? Capital H of ST. and we're going to construct this together. We want it so that h of 0, okay, we'll just go together. So we have f of, well, we want f of 2s to go to 4s. Alright, so it will be basically f of 2 plus 2t times s, because when t is 0, we'll get f of 2s, and when t is 1, we'll get f of 4s. For s between, well, 0 goes to 0, that stays the same, and a half goes to a quarter. So they're both the key insight here is that they're both divisible by 4. This is just this is just 2 over 4. Or in other words, we'll have 2 minus t over 4, because when t is 0, we'll get 2 over 4, which is a half. And when t is 1, we'll get 2 minus 1 over 4, which is 1 over 4, which is here. Right, so that's the f part done. Now we have g of, well, we want g to go from 4s minus 2, wait, what? 4s minus 1, sorry. That should be a 1. Okay, so we want it to go from 4s minus 2 to 4s minus 1. So we have 4s minus, and then we'll have 2 minus t. Okay, because when t is 0, we'll have 4s minus 2. When t is 1, we'll have 4s minus 1. Right? And this is for s between, well, we want it to go from a half to a quarter. Okay, so we'll use the same method we did to take this a half to this a quarter. 2 minus t over 4. Okay, because when t is 0, this thing will go to a half, and this one will go to a quarter. And we want to go from 3/4 to a half, so instead of minus, this will become, instead of a 2, this will become a 3 minus t over 4. Okay? Because when t is 0, we'll get 3 over 4. When t is 1, we'll get a half. Perfect. Now we'll have h of 4s minus 3 going to 2s minus 1. So, first of all, let's deal with the 4s going to the 2s. So, we can have 4 minus 2t times s, because when t is 0, we'll get 4s. When t is 1, we'll get 2s, okay? And then this minus, well, we want to go from 3 to 1, so we'll have 3 minus 2t, okay? Because we'll have 4 minus 2t, well, when t is 0, this thing goes to 3, this thing goes to 4s, and when t is 1, this thing goes to 2s, this thing goes to 1, alright? And this is for s between, well, 1 to 1, so 1 stays here, and we're going from 3/4 to a half, so we'll have 3 minus t over 4. And with this homotopy that we've constructed, we deduce that f star, also yes, don't make fun of my writing, I know it's slanted, okay. We have f star g star h being path homotopic to f star g star h, and so their equivalence classes. Okay? Are path homotopic. And we've now proved that this operation satisfies the group axioms, and we're ready to introduce the fundamental group. With this build-up, okay, now we have the definition of the fundamental group. So, well, not quite actually yet. First we have to define a loop, which is just a path. A loop is a path, P, which takes you from the interval to the interval, such that P of 0 equals P of 1 equals some point x0, which is called the base point. So basically it's a path, alright, it's a path with the extra property that it ends at the same point that it starts. Alright? Now, the fundamental group, which is denoted pi 1 of a space x at some base point x0, okay, under the operation which we defined and showed had all the properties of a group, okay, the fundamental group is under, this is the set of all equivalence classes of loops F at base point x0. And I'm going to erase this definition. We're going to look at computing the fundamental group of some special spaces, such as the circle, which is very important and has some immediate applications of some substance, and one very trivial computation of the fundamental group of the real line. That will be in the next video, okay? For now, it's natural to ask, well, does this fundamental group depend on the base point? Does it matter what base point I pick? Well, this leads us to the definition of an induced isomorphism. So if we let P be a mass that takes you from x0 to x1. Now, this P induces an isomorphism P hat, which takes you from the fundamental group of x based x0 and takes you into the fundamental group of x at x1, okay? And this is an isomorphism. Alright, and the proof is pretty simple. Alright, so P hat, it's defined such that P hat of F of the equivalence class of F is equal to the equivalence class of H star F star H bar. Alright? So it's defined under conjugation. Now, P hat of the equivalence class of F star the equivalence class of G, right? We have to prove that it's a homomorphism before we go on to proving it's an isomorphism. Well, this is equal to the equivalence class of H star the equivalence class of F star the equivalence class of H bar star the equivalence class of H star the equivalence class of G star the equivalence class of H bar. These two cancel out, leaving us with the equivalence class of H star the equivalence class of F star the equivalence class of G star the equivalence class of H bar, and this is just P hat of the equivalence class of F star P hat of the equivalence class of G, because this bit here is just inserted. Why did I even do this? I don't know. This is the equivalence class of that. Okay, yeah, I don't know. I think I saw it the other way around, so yeah. But yeah, basically this here is equal to that there, right? Normally it's proven the other way around by saying that that, and then you insert that in there, and that's equal to that. But anyway, that's a lot of jabbering, okay? But yes, it's a homomorphism. Now, we have to show that it's an isomorphism by finding an inverse, a homomorphism that's an inverse. Alright, so we define p hat bar of f equal to p hat of the equivalence class of f star h, sorry, what am I saying? The equivalence class of h star the equivalence class of f star the equivalence class of h bar. Okay? Now, if we take p hat bar compose p hat, we have p hat bar compose p hat of f is equal to, well, this is equal to p hat bar of the equivalence class of h star the equivalence class star f star h bar, and this right here is equal to, well, this would be equal to, well, in this case f is this, so this is equal to h star this, h star f star h bar star h bar. And now by the associativity and stuff, you can cancel out these two and these two, so this just equals the equivalence class of f. Therefore they're inverses, and you can prove it exactly the same way the other way around, hence it is an isomorphism. And this is called the induced isomorphism, and this is extremely helpful in the discussion of the dependence on the base point, because this shows that up to an isomorphism, the fundamental group of a point of a space x at base point x0 is isomorphic to a fundamental group of x at base point x1. So yeah, okay, that's the discussion of that. So a space x is simply connected if x is path connected and the fundamental group of x at some base point x0 is trivial. Okay? Okay, so say H takes you from a topological space X to topological space Y, is a mapping such that H of X0 is equal to Y0. Now, we can write this as H taking us from X at some point X0 to Y at some point Y0. Right? Now this function H, this continuous function H, induces a homomorphism. H star of the equivalence class of F being equal to the equivalence class of H compose F. Now, to check that this is a homomorphism, what we have to do is show that H star of F star G is equal to H star of F star H star of G. Okay? Now, how do we do this? Well, this right here, this H star of the equivalence class of F star G is equal to the equivalence class of H compose F star G, the equivalence class of F star G, and this is equal to H compose, the equivalence class of H compose F star, the equivalence class of H compose G. And this is equal to H star of the equivalence class of F star H star of the equivalence class of G. Voila! It's a homomorphism. So, a theorem about these induced homomorphisms is that if we have H, which takes you from some space y at y0 to x at x0, and we have G, which takes you from x at x0 to z at z0, then the induced homomorphism of H compose G is equal to the induced homomorphism of H compose the induced homomorphism of G. Now the way to prove this is we have H composed G star applied to some F. Okay? Now by the definition, this is equal to the equivalence class of H composed G composed F, which is equal to the equivalence class of H composed G composed F, and this is equal to H star of G compose F, and this, sorry, for some reason I can't, yeah, there we go, and this is equal to H star compose G star of F. Nice. Now I'll have one more theorem, or corollary kind of, which connects these isomorphisms and homeomorphisms, which is quite a cool connection. Last corollary is quite important actually, okay? Because this will have some nice implications, right? And the corollary is, if H, which takes you from x to from x at some base point x0 into y at some point y0, if this is a homeomorphism, alright, homeomorphism, not homomorphism, homeomorphism, then H star applied to some F is an isomorphism. Okay, and if this is true, well, then two topological spaces which are homeomorphic will have isomorphic fundamental group. We still have to prove it, and this goes as follows. Because H is a homeomorphism, we have H inverse, and from the last theorem, H star compose H inverse star is equal to H compose H inverse star is equal to the identity in Y star is equal to the identity in the fundamental a group of y at some point y0. And you can do the same thing for x. So we have H inverse star compose H star is equal to H inverse compose H star is equal to the identity in X star is equal to the identity in pi in the fundamental group of X at some point x0. So the implication of this is that two spaces which are homeomorphic have isomorphic fundamental groups. And this is really important. But as I said in the last video, in the next video, I'm going to be looking at calculating the fundamental group of the circle. Goodbye.